We talked a little bit about electromagnetic spectrum, but we really didn't define it. So now let's really talk about the electromagnetic spectrum. So let's say we have light, and in this case we have this white light, and we pass it through a slit initially, and so that allows us just to get a really nice kind of spectrum of the white light. Okay, and then it passes through a prism. The prism can separate the white light into its colors, and this is called the continuous spectrum, since we have a continuous display of light. So we have red, orange, yellow, green, blue, purple, all the way down to violet. So this is known as the continuous spectrum. Notice how there's no gaps in the light source. It just goes purely from red to violet. So what we see is known as visible light. Visible light is part of the electromagnetic spectrum. But this is an extremely, extremely, extremely small portion of the spectrum. The spectrum includes a ton of different wavelengths. So let's look at that next. Okay, so what we saw when we were looking at the continuous spectrum is from the red to purple. This red to purple is known as visible light. So that's right here. Okay, visible light takes into account only from here to here, that wavelength. Now, this entire thing is known as the electromagnetic spectrum. So you have this huge, huge range of different wavelengths, and we can only see a really, really small part of the electromagnetic spectrum. Okay, now let's look more at this area. So on the left side, notice the waves. Are the wavelengths going to be very long or short? On the left side, they're going to be very long. They're long wavelengths. Remember, wavelength is defined as from crest to crest. On the right side now, notice these wavelengths. These are going to be very, very small. So we would say these are short wavelengths. Okay, now if on the left side, if these are long wavelengths, what would we say about the frequency? We would say that the frequency would be very low. Okay, so then on the right side, if we have very short wavelengths, we would say that would be very high frequency. Okay, and then let's look at the energy. Which side would have the highest energy? On the right side. I'll denote energy with a big E. And on the left side, it would be low energy. Now you need to know roughly this area. So you need to know high versus low frequency. And what that means is you would need to know that radio waves are going to have the lowest frequency. The next lowest frequency would be microwaves, then infrared, visible, ultraviolet, X-ray, and gamma. So let's look at all of these different types of waves. We have radio waves. That is the first type of electromagnetic wave. The second one are microwaves. Third, infrared. 4, visible. 5, UV. 6, X-ray. And the seventh one we can have are gamma rays. So gamma rays are going to have that highest frequency. So you not only need to know frequency, but you also have to know high versus low energy. So gamma rays would have the highest energy. And then you need to know their wavelengths. The longest wavelength would be radio waves, and you need to know them in comparison. You do not need to memorize these times 10 to the third, times 10 to the negative first, the wavelength in meters. You don't need to know that. You just need to know them in comparison to each other. So there's 7 electromagnetic waves that you need to know. I hate memorizing, right? So I have this mnemonic way to remember it. Rich men in Venus use X-ray guns. So R would stand for radio waves, M would be microwaves, I infrared, V visible, U ultraviolet, X for X-ray, and G for gamma. Okay, now as we're going from left to right, we are going to be increasing in energy. So on the right side, we have high energy, which would also denote high frequency, and short wavelength. All right, again, you need to know this in comparison to each other. And just kind of a fun fact here, high energy electromagnetic radiation could potentially damage biological molecules. So if you are into, like, let's say like tanning beds, that kind of thing, those give off ultraviolet radiation, which is very high energy, which can cause skin cancer. Now gamma rays, those are nuclear type of rays. Some can travel right through the body, other times they kind of stay in your body and they can never leave. So those could potentially damage biological molecules. Now that we've talked quite a bit about light and we looked at the properties of light as in the waves, we've looked at frequency, wavelength, amplitude, and energy. Let's see how that relates to matter. Remember, matter is composed or has to be made up of 2 things. What are those 2 things? Mass and volume. Okay, so atoms, which is the smallest unit of matter, can acquire extra energy, but they must eventually release it. When atoms emit energy, it usually is released in the form of light. Ah, there we go. This is the light's relationship to matter. So when atoms gain energy, they eventually will emit it because they don't like to have a lot of energy. They'll like to go to a ground state, and they emit that extra energy in the form of light. So a lot of times we will see light being re-emitted in fireworks, okay, or neon lights. We are actually going to do a lab, and this is one of my favorite labs, and we're going to explore this topic further. Emission spectrum. However, atoms don't emit all colors, only very specific wavelengths. So remember, when atoms gain energy, they'll re-emit that energy in the form of light, and only certain atoms will emit specific wavelengths. When that emitted light is passed through a prism, so just like what we had seen before, when light goes through the prism, a pattern of particular wavelengths of light is seen that is unique to that type of atom or molecule, and that pattern is called the emission spectrum. Okay, so when the light goes through this prism, we can only see specific wavelengths. For example, we can only see a blue wavelength and, let's say, an orange wavelength. So they'll get separated, but why? We're going to explore this, why we only see specific wavelengths being seen. But this is called a non-continuous spectrum. The reason why it's called non-continuous is we see only specific wavelengths. When we pass white light through a prism, we saw the entire spectrum of the rainbow, right? When we pass light that is from, let's say, only helium, we can only see specific wavelengths. And this can be used to identify the material. We are going to use flame tests, or I should say people use flame tests to see what kind of compound an atom is based off of the colors that are seen. The emission spectra of hydrogen. So this is going to be a better way of depicting what the non-continuous spectrum looks like rather than me trying to draw it. Okay, so let's go through it. On the left we have a hydrogen lamp. So this lamp is filled with hydrogen and we supply some energy to it so that it kind of burns, right? When the hydrogen in the lamp burns, it gives off this, I don't know, cherry-ish color. Not completely red, but it's kind of a mixture of different colors. Okay, we pass it through a slit, so we only get like a really nice selection of it. And then we pass it through a prism. The prism allows us to separate the different colors of light. So it separates the component wavelengths. And we would see that it separates them into different colors. Now we can have this photographic film, is what it's called, and it can pick up just the certain wavelengths that are produced. So we would see that we would get like a roughly an orangey color, denote with a O. We'd also get like a blue color, and then we would get maybe a darker blue as well as a purple color or a violet color. So hydrogen will only give off these different wavelengths. Notice that we don't get a yellow, we don't get a green. Okay. So this photographic film we can use to look at different atoms. So hydrogen, we kind of went through that already. This is A. So if you burn hydrogen, you'll get the orange wavelength, kind of the blue, and then the darker two blue/purple. Helium light, if you burn that, you'll get those wavelengths that you can see in, let's say, the photographic film B. For neon light, look at how many wavelengths you can get. You can get almost a continuous spectrum, although it's not continuous. Notice that it's not the entire spectrum. There's a lot of black parts in there. So that is why you see a lot of neon lights composed, or instead of, let's say, hydrogen light. Because neon light, you can get a lot of different colors. You can get red, orange, yellow, green, all of those. Okay, and I want you to write that these are non-continuous spectrum. We don't get the full wavelength of color. More about the emission spectra. Once the discovery that energetic atoms emit light of specific wavelengths, chemists began cataloging various elements. This helped in identifying elements in minerals and other substances. But some questions were still unanswered. Why were only certain wavelengths produced? Why not a continuous spectrum? Why did they always see these non-continuous spectrum in all of these atoms that they were doing flame tests to? And what accounted for the atom's fingerprint? So the atom's fingerprint is that photoelectric film that they used. No matter if it was helium from the west coast versus helium on the east coast, all helium would give off the same wavelengths. So this was known as their fingerprint. So what accounted for the atom's fingerprint? We will first take a detour to answer these questions and then come back to the emission spectra. So we are going to first look at an atom.